Yeah, thank you, Shira. I'm really pleased to be here and meeting all of you. And I'll just take you briefly through the fundamentals of data science. Basically, the main question is defining data science. There are various schools of thoughts on the term data science. The chief economist of Google viewed data science concept in terms of statistics, where he said it's the ability to take data, to be able to understand it, process it, and extract value from it, and visualize it, and communicate it. And he saw it as a very potential job in the next 10 years, not only at professional level, but also at various stages in the learning process, from the elementary, high school, and up to college level. However, Mike saw the concept as not only focusing on statistics, but also the three key skills on being statistic, data managing, and also visualization. Another thought on data science focused on creating the data products, which whether that data is in terms of search items, whether you have voice samples or product reviews, the users in a feedback loop contribute to the products that they use. And that's how they saw it as a fundamental concept on data science. But again, another thought is that when you use the term data science, it's not the data. The key thing is on the science. Okay? It's mainly about the science. It's measured on the scientific questions that you try to answer using data. Then our very own Neil, on his very famous inverse probability blog, he defined the field of data science to be the challenge. There are a lot of challenges on data, on making sense, mainly on the large volumes of data, that we have a lot of data now being available, enabled through the data from sensors and also the high interconnection bandwidth. So it differs from traditional statistics in that the data, when it's collected, it's not when the process of collecting data does not have the purpose or the experiment in mind. You try to create value on, you try to extract value from the data later on. Okay? So basically, the key question on data science is trying to answer a concrete question using data. So you formulate that quantitative question that can be answered with data. You collect the data and clean it. Those are the usual roles of the data scientist. And then you analyze the data and communicate. You communicate it to answer the question to a relevant audience. So basic thing is, how do you use data to answer a concrete question? And this is a very famous example on data science. Is the Moneyball movie. The data science problem that was viewed from this example is that, can we build a winning baseball team with really a limited budget? So the data that was used was mainly the various players' skills. They used players' salaries, and also all the kinds of data that was used to analyze, do the quantitative analysis there. But at the end of the day, you have to be able to respond to that key question as to whether you are able to build a winning baseball team with a limited budget. There are trade-offs when it comes to data science, where we have various intersections between the data scientist and the data engineer. I'm glad we have both from ARM. They have various roles, and they do intersect when it comes to doing programming, math, and the statistics. Normally, when discussing the various concepts on data science, the engineering part is normally not discussed. But actually the data engineering part deals with the actual implementation of the technology, whether it can be deployed at, if it can be scalable or can be viewed, the technology can be accessed by a large number of people at the same time. And the various functions of the data engineering part is the database administration, storage, and the actual system implementation. Whereas a data scientist is the one who actually learns on the data to visualize it and also doing the modeling based in conjunction with the expert domains to actually develop the model, and then it's implemented to a relevant audience based on the various requirements. Also, there are trade-offs during the implementation that forces one to make the right decisions, whether the technology is interpretable and simple or interpretable and accurate, or whether it is interpretable and fast or interpretable and scalable. So at one time, a data scientist has to make a decision based on these main facts, whether it's interpretable, simple, accurate, scalable, and fast. So those decisions have to be made based on the model that you are working on to achieve the required goal. And when you look onto the domain of life sciences, I've taken that, there is a demand, and there are various the big data challenges in that domain. For instance, we have novel discoveries in the various sectors of healthcare, agriculture, food security. There is data for over 1.2 million species of plants and animals, all available. So as a data scientist doing end-to-end data science, how do you achieve value from that available data? What question are you trying to answer from all the data that is currently available? There is also disease surveillance and response is another domain. Management of health data, electronic health records and experimental data. They can inform diagnosis and treatment using precision medicine. And also, however, the challenges are there, which are the volume, variety, and veracity, to mention a few. So another data sciences includes the biggest, includes statistics, which is basically deals with analyzing the data. Okay, and there are great overlaps with data science, machine learning, and of course the traditional and statistical analysis. However, the key activities that define statistics in the data science domain include the descriptive statistics, explanatory data analysis, quantification, summarization of the data, and clustering. Okay. We also do inference, which involves estimation, sampling, variability, and defining populations. And we have prediction, where we have the machine learning, supervised learning, and supervised reinforced learning. Experimental design, where the process of designing experiments. There are overlaps. There are a lot of overlaps, especially on inference and prediction. However, in this case, I look on the descriptive statistics. They do provide insight when you start working on the data. It does provides a lot of insights before you continue with the other processes of starting developing the model and stuff. For instance, in this work on a Pearl project, which was based on developing decision support tools for small-scale dairy farmers in the East African countries, we could create value from the descriptive statistics, from the summary statistics, where here, sorry, the fonts are a bit small. However, you could see here the farmers, for instance, in Tanzania, in Iringa region, a farmer had 2 cattle in a land size of about 5 acres, which is a big land size compared to the number of cattle they keep, which led us, the same case was viewed in Uganda. A farmer in Chiruhura had 3 animals in a land size of about 10 acres. So what insight do you make from that? That's just the quantification and summarization of the data from these farmers. It actually led us to make this decision that the land size is not proportional to the cattle owned by farmers. So these farmers are involved in other activities besides dairy, okay? And that further led us to find what those other activities are. So the summary statistics on the crops which are cultivated by these farmers on the land that they have for both, for all the 3 countries. Here we had for Uganda and Kenya and Tanzania. We see from the summary statistics in Tanzania that farmers mainly cultivate food crops on their farms. They cultivate mainly food crops, followed mainly by leaving the land fallow. They have fallow land, and also they do grow a little bit of fodder crops. From the summary statistics in Kenya, the Southern Rift, the crop that the land is mainly used as a grazing land, which you can infer that maybe the land in the Southern Rift is not as much arable for cropping, which I'm sure the Southern Rift is quite mainly for grazing. So you could tell, you can tell that from the summary statistics, and then when you compare with what is actually happening in the ground, they do correlate. In Uganda, we see food crops are mainly grown in the Wachiso. They grow a lot of food crops, followed by Mbarara and Chiruhura. And when it comes to grazing grasses, they are mainly they're mainly found in the Chiruhura region. And I presume in Chiruhura it's drier compared to the Mbarara and Wachiso. We have a lot of food crops grown in Wachiso, which means the land in Wachiso is more fertile. That's where the arable land is, which is really matches. So you can really use data to clarify what is happening on the ground. And the same in Tanzania, Arusha, Iringa, Kilimanjaro, Mbeya, Njombe, and Tanga. These actually are the food baskets regions in the country. That's where a lot of food crops are grown. And when we look at Mbeya, they leave a lot of their land for fallow. They have big land areas. And another reason for having less land for grazing in other regions, it could be the area is mainly the urban areas. So in urban areas, you have limited land for grazing. That could be another reason where there aren't many grazing grasses grown. So from the summary statistics, the descriptive statistics, you can really tell a lot about the area. And then we compared the situation at in the three countries. And actually, this data set has 20,000 farmers, and the data was collected for a period of about a year and a half. 20,000 farmers. We had enumerators sent at the dairy farmers in the countries, and all the data collection was digitized using the ODK toolkit. And another analysis done, the summary statistics were also done on the traits. What are the leading traits of dairy farmers? What do dairy farmers look into when it comes to their own cattle? So here we see the leading trait being milk capacity, milk quantity is normally the trait that dairy farmers go into. And that is followed by disease, what's the resistance to disease. So this was also done using rank analysis to be able to find the traits this was for Uganda, for regions in Uganda. So another broad area within data science is machine learning. And basically, machine learning is the principal technology underpinning the recent advances in AI. And we know machine learning is a subdomain of AI. And it deals mainly with, you have data. How do you model the data? Okay, what's the hypothesis and the loss function defined mathematically, and the computational power that's required based on the size of the data. Then you can predict you can perform the prediction. But machine learning methodologies, they are mainly dependent on models and the mathematical models. We have access to large amounts of data with which is basically owed to the high interconnection bandwidth. However, we receive much of this information through computers. And we have a new information flow once the data is processed, and once the data is also processed. And the famous example when it comes to machine learning is the regression model for predicting the Olympic gold medalist. Okay, this is normally done. This was done using regression with data collected, historical data as far back as 1920, and the model fit is done to find the time that will take a runner to win a gold medal. So it's all mathematical modeling, and the Olympic gold medalist was done using regression modeling. Further, machine learning takes the approach of observing a system in practice and emulating its behavior with mathematics. One of the design aspects in designing machine learning solutions is where to put the mathematical function. Based on the data you have to decide on which mathematical model best fits your data. And it really builds up on complexity, and also the design process requires a lot of imagination. And then we have the three classical approaches to machine learning: the supervised learning, unsupervised, and reinforcement learning. And we'll cover, each aspect will be covered through the summer school in the next few days. Practically, every aspect will be covered in detail. Where in supervised learning, you learn a model from a given set of inputs and output pairs in order to predict the outputs of the new inputs. It is normally grouped into regression and classification, which will classification problems. In unsupervised learning, you have to discover the patterns and learn from the structure of unlabeled data, and clustering mainly falls onto that. In reinforcement learning, you have to make decisions on the actions that you need to take in a given situation based on rewards and penalties. Okay? And this gives the basic differences between the machine learning and traditional statistical analysis. And machine learning focuses mainly on predictions, where in statistical analysis you mainly focus on the population inferences. And you normally focus on prediction via prediction performance when it comes to machine learning, where you rely mainly on hypothesis, a priori hypothesis when it comes to the traditional statistical analysis. And it emphasizes on performance of the model when it comes to machine learning, whereas in statistical tradition, we mainly focus on parameter interpretability. And now, how do you combine all these concepts, statistics and machine learning, to achieve end-to-end data science? So these are the main components that you have to define the goal. What is the fundamental question that you are trying to answer using data? So you have to first to define your goal, and then you prepare the data. That means the data preparation involves even the data collection and also the cleaning. And then there comes now the data science part. The data science part involves the feature selection. You develop the model, train it, and you validate it before you deploy it. And this is not a linear sequence, because even after you deploy the model, there are issues that may arise, okay, and questions that need to be answered. So it's not a linear, it's not a directly linear sequence. It's like it involves quite a number of loops. It's a looping process. That's the reason the arrows are not only pointing in one direction, but they do go back. It's a loop process. So that's how it's end to end. So these are, when you adopt the predictive analytics approach in an end-to-end data science challenge, you have to define the goal. And then you have to understand the data and prepare it. As we defined earlier, at times when the data is collected, you do not have the fundamental objective yet. Is normally which comes later, and these are the processes which are involved in understanding and preparing the data. You have to import it, clean it, manipulate, and visualize the data. And then comes the process of building your model, machine learning model, which involves the feature selection. You select the features which are relevant to answer your question. You train the model, and also you validate it, and then you deploy the model. But again, this is not a linear sequence. It does involve loops because of issues and questions which may arise on the model behavior on deployment. I think that's a very brief introduction, and this is the end. Thank you. Yeah. Yes.
Maybe could you say a little bit about the difference between a kind of a one-time analysis to answer a specific question and putting into place a kind of, I guess, a deployed system that's going to produce like a monthly report every month or something like that, and maybe what, particularly your last diagram seemed to speak to that.
Okay.
So much more work to deploy the system.
Yeah, and actually whenever you deploy the system, a lot of questions do arise. For instance, I'll just use a recent example of some work which is still in progress. That you have, when you have a model of weather prediction model, okay, for predicting weather at a particular location. And the motivation for this work was to have the weather information offline. But again, you collect the data, historical data from the satellite data, and develop a model, a mathematical model for predicting weather in a period, say, of a week. And then the model is deployed. And the features which are mainly selected would be minimum temperature, maximum temperature, could be humidity at the place. It's mainly to be able to allow farmers to have the first-hand information about the weather, so that they can predict whether the diseases are coming from having high humidity or lower temperatures, just to foresee that. So those are the features that you select to report on when it comes to weather, predicting weather in the short time. And then you train the model. It could be a time series or a regression model based on the data. And then you validate the model. And compare it to the actual temperatures which predicted by the standard weather stations in the world for that particular location. And then when you deploy the model, for farmers or extension officers to use this model at that particular location, then when it's on site and they're using that tool to be able to get the weather, it might reach a time that after a period of use, some issues might rise that they use that tool with the various weather being predicted for a certain period, and then, however, it may, after a period of time, that model may not behave properly compared to the actual temperatures which are being given by standard weather stations. Then one will have to again sit and see how you can train the model again with a new set of data set which is released. You can now, the frequency of one training your model could be monthly or maybe after every 3 months. So you have to go back up to the model training. Or farmers can call upon another feature which will force you to revise your whole model to include a feature, say, on wind speed. So you'll have to revise select new features and then do all the model training, and before again you deploy a new model altogether. Yeah, that's how I put it. Yeah. Okay. Yes, Ernest.
Yeah. So thanks for the talk. I don't know if you have some advice for, maybe imagine a student who's here, sort of looking at all these parts. Now we've sort of talked about the whole pipeline. Maybe they wanted to get into the action, how they start, for example, and if you imagine a student, maybe data sets are not too common, how they sort of get into the action.
Can I ask, this question wasn't asked in the beginning, why everyone's here? Maybe someone wants to be that engineer, so someone is not he will not be dealing with that work.
Exactly. And actually, even the data preparation part is a whole domain on its own. Yeah. Exactly. Yeah. 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 Exactly. Yeah.
Who are the data engineers?
Data engineers, the data scientists, or someone has worked. Yeah, because it's a whole domain. You could get your master's only on the data preparation part. You can attain your degree only on the data, because developing tools that are very much suitable for gathering all data is a whole domain on its own. Yeah.
Huge attention should be put on actually transferring the model or deploying the model or making it understandable, maybe not usable, but somehow it's not kind of focused many people, which I found finding data science. Huge focus on processing the data, the model building, but not making the model understandable and usable by end users.
And the end users are defined based on the they just want the end product.
Exactly. And the end product will be A/B. As simple as go to place A, do action B. That's it. So they don't care about the model. I guess the question is how to make your results of your analysis actionable.
Usable to the end user, to be adaptable. Yeah. Yeah, exactly. The model deployment. Yes.
So my question is around, you touched on the difference between the descriptive statistics and machine learning. You said something about one where you're able to know what you're expecting and the other not being able. But also, generally, as somebody who has not gone deep to data science, And there's a whole issue of statistical learning, machine learning. Just throw some light around those areas. Is it a difference in methodologies? Is it a difference in the statistical learning, machine learning?
Yeah. In the big picture, you say we have those main branches of the statistics, but now the technology you use, the approach you use in analyzing the data, it's the same data, but we can use the summary statistics in descriptive statistics to get an overview of how the data looks. And you can, with descriptive statistics, you can now even define which domain should go further in the analysis, in the modeling, which characters, based on the goal that you want to achieve. Like here we were trying the descriptive statistics, which I gave the example on, we're trying to develop tools that will enable smallholder farmers in dairy sector perform better. But now what are those factors? That's why we had to look on all those aspects on the land area they have in relation to the number of cows they keep. Now, further, when you go now to do the modeling part where you apply now the machine learning techniques, which is mainly the modeling using the data. Now, from the summary statistics, they do inform you on which now variables to use in the modeling, which are those aspects which really define a dairy farmer. Is it the land size? Is it the cattle head? Is it the diseases? What traits are they looking into when it comes to dairy? So all that is informed using that. But with the summary, you explore. Because when you start the experiment, you have all the data, but you don't have the insights yet. Yeah, so machine learning goes deeper than the descriptive statistics now to actually model, develop a model that will predict the future of those variables, answering the fundamental questions in the domain. Yeah. Yes, Damon.
We'll have a session on deploying models.
Exactly.
We'll talk about techniques and tools to make it easier to serve models in production.
Exactly.
And from the comments here, I'll touch on visualization as well as a form of production.
Yeah.
And then the other comment is the separation between data scientists and data engineers is great in a big company or a big research institute. But the fact is when you start a small project, when you're one person or two people or a startup,
You have to do all.
doing it everything. So I think it's very healthy for everyone to at least be aware of the whole end-to-end stack. Because also when things go wrong on the data engineering end, it's very helpful for the data engineers, the data scientists can actually understand why it's going wrong. So yeah, I think it's going to be good.
Yeah, and we're very lucky to have both here with us from yeah. Okay. Yes.
I think to contribute to what you have said, this descriptive statistics is better when you mention it as exploratory analysis, what you're from enterprise.
Yes.
Because the descriptive statistics, you are restricting yourself to these summary statistics. But when you use the term data, you use that philosophy of data analysis where you explore the data to give you the insight into what you wanted to use.
Yeah.
As you go ahead in your analysis. Because there are a number of philosophies of data analysis. That is the classical.
Yeah.
That is the old way. Those people studying long time ago.
But if they change, they become, yeah.
The modern statistician or data scientist who now are the data category. That is the philosophy where you let the data, where you explore the data, tell you what you wanted
To use.
And then there is the Bayesian group now, which is the most complicated category of people. Yeah, because they have to make some assumptions or prior assumptions. And to explain what they wanted. So I think the best term is that exploratory analysis. I'm sure because the descriptive is restricted us to figures. But the error opens it up.
Qualitative. Yeah. Okay, thanks for that contribution. Yes.
I would like some clarity on the difference between prediction and
So I wonder why these two are not the same sort of.
Yeah. Can you help me with that? Inference and prediction. As I said, there's quite an overlap. There's quite an overlap between on them. Yeah, as I said earlier. It differs, I think, on the nature of the data and the technology you apply, whether it can be fit on prediction or inference. Inference mainly focuses on the population data, whereas prediction does cover the historical data as well. Yeah.
I guess inference would be the bigger thing. I think
The bigger
would
thing.
be
Mm-hmm.
Part of inference. I think to infer
Yeah.
things is given some data.
Mm-hmm.
To infer some new maybe knowledge, or some
Insights.
relationships,
Mm.
or some.
Yeah. Yes.
Often inference is also aimed at trying to make a decision.
Mm-hmm.
If we were considering alternative interventions that we might make in agriculture, we would consider liming fields versus more irrigation, something like this. We would want to try to see which interventions have been more successful according to our data set. Okay? And we might do that by looking at the regression model and how much impact it would predict from if you change the amount of this variable, what the impact would be. So it relates maybe also more to causal inference, which is a topic where I guess traditional statistics, they wanted to make causal inferences that smoking causes cancer or these kinds of things, or what is, we were just discussing earlier today, about what is causing the particulate pollution that we're seeing. And so those are the kinds of, and that's much more than just prediction. In fact, really,
It's
because
bigger.
you are trying to make a prediction, but about some action that you might take. So some change in the world, not just to observe.
Thanks for that, Prof. Tom. Yeah. Okay. Thank you. Program chair.
Shall we take just a longer break? Cool, Shira, what's the plan next?
Yeah.
Shall we take a longer tea break?
I have a small plan. Do you have another plan?
So no, there's a program online. I hope first administrative things. I know you're almost shaking because of no Wi-Fi, but there is Wi-Fi. I think you've seen a router there. So it's Data Science Africa, and but now if you all log on at the same time, I think I'll give the password to this side, and then later to this other side. But okay, Data Science Africa, and the password is 2018 Data Science. Small letters, all one word.
Yeah, strong passwords.
So, but just following, so you can log on to the website. The program is on the website.